Welcome to ES 310 Lesson 36. Today we will complete our look at vibrations by dealing with systems with damping. So we have vibrations, either free or forced, that will die out due to friction. More information about this topic can be found in Hibbler's Dynamics textbook, chapter 22, sections 4 and 5. So as a review of vibrations that we saw in the last lecture, we have free vibrations, which are due to the initial conditions of a system. So a block might be displaced by a certain amount or given an initial velocity. The standard form for the equation of motion has a 1 in front of the double dot term, and the coefficient of the non-dotted term is omega n squared. And that's equal to 0 in the case of a free vibration. The solution of this is that x is equal to a sine omega nt plus b cosine omega nt, or it could also be written as c sine omega nt plus phi. For the special case where we have a block sitting on a single spring, omega n is equal to the square root of k over m. In the case of a force vibration, we have a force that's pulling and pushing on the block. In addition to the free response, we will then have a term that is due to this force. Most real systems, the free response dies out, and we are left only with the forced response. In this case, the standard form of the equation once again has a 1 in front of the double dot term. The coefficient of the non-dotted term is omega n squared. And then on the right-hand side, we have the forcing function. So we have d naught, which is whatever the coefficient of the sine or cosine term is. Omega naught is the forcing frequency, the frequency of the forcing force. And so from the standard form, we can find omega n, we can find d naught, we can find omega naught. To find a and b in both of these equations, we use initial conditions. So if we're given an initial condition that x of 0 is equal to some number, then we plug in 0 into this equation, set it equal to that number, and solve for the unknowns. We are also usually given a velocity, so x dot of 0 is equal to some known. So we take the derivative of this expression, plug in t equal to 0, and solve for the unknowns. In the case of forced vibrations, we have a multiplication factor, which is the ratio of the output and the input amplitudes. And that gives us the amount of increase or decrease, increase if it's bigger than 1, decrease if it's less than 1, of the motion of the block due to the fact that we are forcing it to vibrate. It's given in terms of the ratio between the forcing frequency and the natural frequency. The closer the forcing frequency is to the natural frequency, the higher the magnification factor is going to be. What we are adding in this lesson is viscous friction. So this is called damping because it dampens out the vibration, so it slowly decreases the vibration. And we are dealing only with viscous friction, which is proportional to the speed. So the faster an object is going to go, the higher the viscous friction is going to be, which is usually due to some form of drag. And so the force due to the damper is equal to c, which is the coefficient for the damper, times x dot, or the velocity. If we write the equation of motion in standard form, once again we have 1 in front of the x double dot term. Now we have an x dot term that has a coefficient, and we have an x term that has a coefficient. From this equation, we know that we can find the natural frequency from the coefficient of the x term, and we can find this new coefficient, which is called zeta, which is the damping coefficient. In the special case where we have a 1 mass, 1 spring, and 1 damper, omega n is still the square root of k over m, and zeta is equal to c divided by 2 times the square root of k times m. This damping coefficient is based on all 3 values in our system. There are 3 possible conditions for damping, for the damping coefficient. damping coefficient can be equal to 1, in which case we have critical damping. It can be less than 1, or it can be greater than 1. So the critical damping, zeta is equal to 1. If we plug in 1 for zeta, we can solve for the critical damping value, which is equal to 2m times omega n, or 2m times the square root of k over m. As a reminder, this is only for a system where you have a single spring, a single mass, and a single damper, which are all in series. For any other situation, it is true that zeta is equal to 1, but it will not be necessarily true that the critical damping value is equal to what's given here. So, as we were saying, there are 3 possible solutions. So, the overdamped case is where zeta is greater than 1. In that case, x, the value for the solution to this equation of motion, is a e to the lambda 1t plus b e to the lambda 2t, where lambda 1 and lambda 2 are given by these expressions. So that's the overdamped case. The physical picture of an overdamped case is that there is no vibration. Because these are both dying out, there's no sine or cosine in this solution, so there's no actual vibration. If we hit it with a hammer or we excite it in some way, the motion simply dies out. Critically damped is where zeta is equal to 1. In that case, our solution is x is equal to a plus bt e to the negative omega nt. The third possibility, which is the most common, is where it is underdamped. In this case, it's going to vibrate, but those vibrations are eventually going to die out. So let's look at underdamped case in more detail. The condition, once again, is that zeta is less than 1. The solution to this, in 2 forms, is that d, some unknown coefficient that we would need to identify from the initial conditions, is times e to the negative zeta omega t times the sine of omega dt plus phi is our solution. We can also write that out instead of using phi, using a sine term and a cosine term. And once again, we would find a and b, or d and phi, using initial conditions the same way we did before. Now we've introduced a new quantity. That this omega d is called the damped natural frequency of our system. Because there is damping in our system, the actual frequency of vibration is not omega n, but is shifted slightly because it's damped. And so omega d mathematically is given by omega n times the square root of 1 minus zeta squared. And zeta, again, is less than 1 for this situation. So this is a graph of what this motion would look like. So if you imagine this being a mass on a spring in a damper system, you pull down on the spring and you let go, and you get a big vibration, and the second vibration is slightly smaller, and the third vibration is slightly smaller than that, the fourth vibration is slightly smaller than that, and you get smaller and smaller and smaller and smaller until it's practically 0. The period of vibration for these is measured from a peak, from a maximum to the next maximum, and is given as 2 pi over the damped natural frequency. So let's take a look at an example of damped vibration. We have a T-bar, and it is going to be rotating theta. And we pull it down theta, we let go, the spring is going to pull it back up, and so it's going to swing back and forth. And so I want to draw this T-bar in a displaced configuration, so I'm going to exaggerate this a little bit, right? And so here's our beam, and it's been moved down a theta. That same theta is in here and over here. Alright, if we pull it down, then the spring is going to be stretched, so it's going to be pulling it back up. And that force is Kx. We've pushed up the damper, so the force is going to be down, right? We're pushing up on the damper, so the damper is pushing down on the T. And that force is Cx dot squared. And this x1 and this is x2. Because of symmetry, those x's are the same in this case, but if this 0.3 were not the same as that one, they would be different. And then we also have gravity. So we have mg acting here. All right, so that's going to be pulling it down, which is going to also restore it to its original position. Right, so this direction is our theta. So those are our forces on this system. So we're looking at rotation, so we're going to use the sum of moments is equal to I alpha. And so the moments caused by these three forces are, we've got kx1 times the distance, which is 0.3. We've got cx2 dot times the distance, which is 0.3. If we look at directions, if theta is the positive direction, then kx is going to cause it to go the other direction, cx is going to cause it to go the other direction, mg is also going to cause it to go the other direction. So if theta is drawn in the positive direction here, these are all negative. And then we have mg, and this distance, right, so we need the perpendicular distance to the force. This distance is the hypotenuse, which is 0.3, half of the 6, times the sine of theta. So this is times 0.3 sine of theta. Now we need to figure out how to write x1, x2 dot, and sine of theta in terms of theta. So let's start with the sine of theta. If theta is small, which it typically is in vibrations, then sine of theta is about equal to theta. And you can prove that to yourself. Take out your calculator, plug in sine of a small number, and you should get that small number back. So sine of theta is going to be approximated as theta. Now, if we look at x1, x1 is the distance that this spring is stretched. All right, and so x1 is going to equal r theta, right, an arc length. So x1 is then 0.3 times theta. Over here you do the same thing. x2 is the distance that this point A moves, and that is going to equal r theta again. R is 0.3. We don't care about x2, we care about x2 dot, so we take x2 dot and we take the derivative of this side as well. So now we can plug all of those things in. I, for this T-beam, we need to find yet. So we've got I for this rod, which is around its end, and I for that rod, which is around its center. The mass of each of these rods, the mass is given as 10 kilograms per meter. Each of the rods is 0.6 meters. So the mass of a rod is 0.6 meters times 10, which is 6 kilograms. So then I is the mass of the top rod around its center is 1/12 mL squared, and the mass of the bottom rod around its end point is 1/3 mL squared. And so we can plug in numbers there. 1/12 times 6 times 0.6 squared plus 1/3 times 6 times 0.6 squared. And we get a value for I of 0.9. Alright, so let's plug in some numbers here. We've got 0.9. Alpha is theta double dot is equal to negative k is 600 times 0.3 theta is x1 times 0.3 minus c is 50 times 0.3 theta dot times 0.3 minus m of this, just this rod, the bottom rod, so that is 6 times 9.81 times 0.3 times theta. If we solve this out with all the numbers, we can reduce it to an equation that is 0.9 theta double dot. We're going to move everything over. Minus 4.5 theta dot sorry, plus, because we've moved it to the other side, plus 71.7 theta is equal to 0. Now we can write this in the standard form by dividing through by 0.9, right, because we want to get a 1 in front of the double dot term. And we get theta double dot plus 5 theta dot plus 79.6 theta is equal to 0. Now if we look at our standard form on the previous slide, 2 slides back, the coefficient of the x dot term is 2 zeta omega n, and the coefficient of the x term is omega n squared. So this term is equal to 2 zeta omega n, and this term is equal to omega n squared. So if this is equal to omega n squared, then omega n is equal to the square root of 79.6, which is equal to 8.9. Plug in 8.9 over here, we get 5 is equal to 2 zeta times 8.9. So zeta is equal to 0.28. So what did it ask us to do? We needed to show that the system is underdamped. Well, 0.28 is less than 1, so underdamped. And we had to find the pendulum's period of oscillation. Well, the period of oscillation, this is underdamped, so it's going to vibrate, but it's going to decrease. So we actually have a damped natural frequency, which is the natural frequency times the square root of 1 minus zeta squared. And if you plug those numbers in, we get, what, 8.9 times the square root of 1 minus 0.28 squared, which is equal to 8.5, so slightly smaller than the natural frequency. And the period then is 2 pi divided by the damped natural frequency. 2 pi divided by 8.5 gives us 0.735 seconds as a period. So the key here is to recognize that once we have it in standard form, the two values that we're interested in fall out, right? The damping coefficient and the natural frequency can be solved for from these two coefficients. And then knowing those two, we just apply the equations on the previous slides to find the solution, or to find the damped natural frequency, or to find the period. Now let's look at the situations where we have forced vibration with damping. So with forced vibrations with damping, the free conditions die out because there's damping. And what we're left with is only the forced equation, part of the equation. So standard equation of motion is mx double dot plus cx plus kx equals f naught sine omega t. This is only for a single mass spring damper system. In general, our standard form equation, divide through, right? And we would get x double dot plus, same as before, 2 zeta omega n x dot plus omega n squared x is equal to some number d naught, just like before, like last time, times the sine of omega t. Alright, so that's our standard form. This is the special case where we only have a single, so this would be our, we have a force, we have a spring, we have a damper type situation. And it only holds for that type of situation. This holds for any situation. Alright, so the steady state solution then, we ignore the free part. Damping has decreased the free part to 0, so we're only interested in the forced part. Its solution is going to be x is equal to some coefficient, x prime, times the sine omega t minus phi prime. X prime is given by this expression. Notice this reduces to what we had last time if zeta is equal to 0. that this term goes to 0. We've got the square root of a squared, so it's just omega n squared minus omega naught squared, which is exactly what, if we go back to this slide, exactly what we have here as our forced solution. So we're being consistent, but if there's zeta, we have an extra term. And same thing with the phi prime. You get tangent of these two expressions, which reduces, if zeta is 0, you get the inverse tangent of 0. Alright, so magnification factor, same as before, same idea. If you have a natural frequency that is close to the forcing frequency, you're going to get amplification. Otherwise, you're going to get something decreased. This is a graph of that amplification. So the x-axis is omega naught over omega n, right? So if they're the same, you've got 1. If you have no damping, you go to infinity. As your dampening increases, you decrease your magnification factor. And the expression is given. It's more complicated than before, but we know all of these things. So the idea is, if we can write our equation of motion in standard form, we can solve for zeta and omega n, we know d naught, and we can then find everything else. Alright, so we know d naught, we know omega naught, we know omega n, we know zeta. And so we can find the coefficient of our solution, we can find the phi for our solution, and we can find the magnification factor. So let's do an example of this. Here we have a block. We're pulling down on it with a forcing function. We have 2 springs and a damper. So if we draw a free body diagram, we have kx going up, we have another kx going up, we have a cx dot going up, right? Because if we're pulling down, these are the restoring forces. Notice we're not using an mg because we're assuming we start with the spring stretched so that it balances mg. And then our x is measured around that point. So if we write our equation of motion for this, we've got the mass times the acceleration, written as x double dot, is equal to minus 2kx, that takes care of those 2 terms, minus cx dot, that term, plus p. Let's move all the x terms to one side. So we get mx double dot plus cx dot plus 2kx is equal to p. Let's plug in all our numbers. We have mass is 30, x double dot plus c is 300, x dot 2 times k is 1500, x is equal to 300 sine 5t. Right, this is not standard form because we don't have a 1 in front of the x double dot, so we're going to divide through by 30. So we get our standard form, x double dot plus 10x dot plus 100x is equal to 10 sine 5t. So from this we can write the coefficient of the dotted term, the single dotted term, is 2 zeta omega n is equal to 10. Coefficient of the non-dotted term is omega n squared is equal to 100. Coefficient of the sine or cosine term is d naught is equal to 10. And the frequency of the sine or cosine term is omega naught is equal to 5. So from this we get omega n is equal to 10, square root of 100. Plug in 10 up here, we get that zeta is equal to 0.5. And so now we have all of the variables that we need to know in order to write the steady state vibration. We found the natural frequency, we found the damping coefficient. We don't know the damped natural frequency yet, so we still need to do that. Alright, so let's write the steady state vibration. That was x is equal to x prime sine of omega naught t plus phi prime. X prime, the expression is d naught divided by the square root of omega n squared plus minus omega naught squared plus 2 zeta omega naught omega n whole thing squared. It's under the square root. Plug in the numbers, we get 10 divided by square root of 10 squared minus 5 squared plus 2 times 0.5 times 5 times 10, all of that squared. Plug that into your calculator, we get x prime is equal to 0.11. Phi prime is equal to the inverse tangent of 2 zeta omega naught omega n divided by omega n squared minus omega naught squared. So the inverse tangent of 2 times 0.5 times 5 times 10 divided by 10 squared minus 5 squared. Plug that in, you get 33.6 degrees, but we need it in radians, so that's 5.588 radians. Plug those two things in here, and our final response is x is equal to 0.11. Sine of omega naught is 5t plus 0.588. And the last thing we needed to find was the damped natural frequency. So omega d is equal to omega n square root of 1 minus zeta squared. So that is omega n is 10 square root of 1 minus 0.5 squared gives us 8.66 radians per second. So once again, we write our equation in its standard form. From that, we can find all of our coefficients, all of our various variables, zeta, omega n, d naught, omega naught. And then we can write our standard form of our solution, solve for x prime and phi prime from the equations, plug them back in for our solution, and then we can solve for omega d because we know omega n and zeta.